Well, this next session is only an hour with three major stars, both in information theory and outside. And each has 15 minutes and maybe 5 minutes for discussion. So I take advantage of their fame and don't cheat them with their time and get the show going. The first speaker.
Don't be tough.
Yeah, I'm going to crack the whip if you go over time. I have long arms. I warn you. The three speakers are Eric Renaud, Duncan Foley, and Amanullah. Eric is the first to go, and I'm very curious about the content of all three papers, and this one is identification of beliefs in the presence of disaster risk and misspecification. Eric, is all yours, 15 minutes.
Okay, thank you, Issy. Can you see my slides?
No, share your screen.
I have shared. Okay, and like that?
There we go. There
okay, right, right, thank you. Okay, so thank you, Issy, for these nice words. Okay, okay, so something does not work as I would like. Okay, let me try. Okay, why can I not? Okay, okay, it can work like that. Okay, so it is an application of Inference about an asset pricing. And I knew that Mike Stutzer is going to talk before me, so I knew that we'll talk about asset pricing. I could not guess that he would talk a lot about Anisha Ghosh. It turns out what I'm presenting today is quite related to her work, in particular a paper she has written with Julia. The point is, in finance, there is a very famous, of course, equity premium puzzle, meaning that most popular asset pricing models are not able to explain how much risk is compensated. Underestimate this compensation. And Julia and Ghosh, in a famous paper, have used an information theoretic framework to back out some probabilities which are in people's minds, so they are basically beliefs, and that may be different from sample frequencies of the event. And thanks to this degree of freedom, they try to reconcile the data with what the model is saying, the asset pricing model is saying about equity risk premium. Okay. And so I will organize my talk in three short parts, hopefully. Number one, I will try to understand the motivation of this kind of work, that is to say, why model implied probabilities that basically deduced from Infometrics may confirm the so-called rare event hypothesis. That is to say, the idea of this literature is to try to explain the high risk premium by the fact that people have in mind some subjective probabilities or some beliefs which are different from what you observe, in particular for the possible disaster risk. The disaster risk, of course, you observe it very rarely, but in their mind, it is not so negligible. And this may explain the equity premium puzzle. And typically, backing out model implied probabilities thanks to Infometrics may be a way to give a quantitative assessment of this intuition. The problem is, the technical problem I'm going to point out today is that, at least if you remain true to the popular setting of empirical likelihood, if there is unbounded disaster risk, and this is basically what people have in mind, you actually cannot identify belief with empirical likelihood. The optimization program, I'm going to explain you why, does not admit a solution. And of course, it is worrying because it means that when Julia and Ghosh typically are computing in sample some implied probabilities from maximization of empirical likelihood, if there is no such thing as corresponding population quantities to estimate, you may be in trouble to interpret the result. So this is the negative part of my talk. hopefully I will have time to go also to the more positive part, even though obviously there are some caveats, but how to deal with unbounded disaster risk. I'm going to explain that. Sure, the solution does not exist with empirical likelihood, but it may exist if you are ready to consider more generally the family of clustered power divergence, which is of course very popular in information theory. And if you look at it with non-negative exponent, by contrast with empirical likelihood, it's going to give you a solution. So I'm going to explain that. Okay. So number one, what is the setting? So basically, I'm looking at a set of n asset returns that I observe at different dates. So I have a vector of returns. And I have an asset pricing model, which is summarized by a stochastic discount factor. And if you are a bit familiar with this literature, basically, what it tells me is that if I multiply a return by a stochastic discount factor, it should give me an expectation of the price of this return. And by definition, since it is a return, the price of the return should be 1. So meaning that if I have the vector of 1 and that I subtract to this product, this thing should have a 0 expectation and even a 0 conditional expectation given past information. It's basically what a well-specified model of stochastic vector is going to give you for some well-chosen value of the parameters theta is going to give you this equality. Okay, so this is a well-specified model. But we are talking about the equity premium puzzle, so we are typically thinking that the model may be specified. So basically what we do is that we minimize, we are fishing for implied probabilities which are different from the empirical ones, which will minimize for a given value of the non-parameters theta, the difference between these implied probabilities and the naive 1 over t, but under the constraint that the pricing equation should be correct in some point. So basically, we are fishing for these implied probabilities. And as you know, of course, there is a complete family of clustered discrepancies. In the limit case gamma equal -1 precisely give you empirical likelihood. The case gamma equal 1 give you squared, so a chi-square distance, so it's called Euclidean empirical likelihood. Gamma equals 0 give you the limit Kullback-Leibler information criterion, and so on. You have a bunch of possible choice of the discrepancy. The point is that with the only case we have closed form formula is the chi-square distance, because quadratic minimization of a quadratic function under linear constraint. So in this case, it is you have a closed form solution, which is this one, which is well known. And we have shown with my co-author again today, Sarah Chaudhuri, is that you have a similar formula for empirical likelihood. The only difference is that it's not closed form because you compute implied probabilities, but they are not only on the left-hand side, they're also on the right-hand side. So this is not an explicit solution for the implied probabilities, but still, it shows you that it has a similar pattern, I would say, that the naive Euclidean case. And in particular, you can use that, it is not my purpose today, but you can use that to compute estimation of any probability, the expectation of any function by just using these corrected probabilities with respect to the naive 1 over t, because they take into account your moment condition. But it's not my purpose today. My purpose today is to look at the implication for that in population. In population, basically, you will compute expectation like that, just deduce from these implied probabilities if you apply the law of large numbers, okay? And so you will get implied expectation for Euclidean likelihood and empirical likelihood, and hopefully, if they exist, implied densities corresponding to this expectation. So basically, you correct the historical density to take into account the fact that your moments are violated. That is to say, the expectation of y of theta is not 0. Your model is misspecified, so you have to change the probability. And of course, the change depends on the discrepancy. So with Euclidean likelihood, with empirical likelihood. Okay. The problem with empirical likelihood, of course, is that since it is not in closed form, you have to get convinced that there exists a solution of this equation. Okay. Before talking about that, let me briefly show you why people have in mind the rare disaster interpretation is that typically assume to simplify that you price correctly the risk-free asset. Then the expectation, which should be 0 if the model is well specified, is you have the expectation of the product, so you have the covariance plus actually the equity premium. Okay. meaning that if the equity premium is, in your observation, larger than you would have thought, it means that this guy, which will be expectation 0, has a strictly positive expectation, right? You have asset by asset, you may have surprise because your asset, you have an equity premium puzzle, the risk is more compensated than you would have thought. Okay. And to go further, there are disaster interpretation. If I look in the case we have closed form, in the Euclidean case, how you modify relatively the density of observation. Imagine that you have just two assets. One is properly priced, so 0 expectation, but it is a bad state. So it takes a value today, which is smaller. And the other one is not properly priced. The risk premium has been underestimated. Its expectation is strictly positive. And you're also in a bad state. You can easily check that more often than not, the probability that you are going, when you are going to revise your probability density function, you are going to put more weight on the bad state. So typically what Julia and Gosh observe is that when they compute implied probabilities, there is more weight for bad state, which is typically the financial intuition we had in mind. That bad state in the belief happen more often than in reality. It's a bit more complicated because you have the possible that since you know that you have a bad state in Y1, in Y2 you can expect even worse, but assume that it is a bad state like that. The control for contagion effect, it is something like that. And you can, so basically what they say is the higher distribution need to rationalize the equity premium puzzle, assign relatively higher weight to a few particular bad states. And it is also true with empirical likelihood and with more assets. You have to look at the precision matrix and to assume a kind of multivariate negativity to control for correlation, but it is basically this way. So now I want to convince you, just be sure to go sufficiently fast. I want to convince you that this may not work. That is to say, the belief you pretend you have to identify do not exist. Let me explain. If I go in population now, basically what you're looking for a change of measure, like looking for a risk neutral as Mike was mentioning, but here it's not a risk neutral, it is a belief measure, where basically you have an implied density implied by the Crest-Series distance you have chosen through a gamma parameter, where you correct the historical distribution, okay? And so you have the Crest-Series family. In population, you minimize the contrast like that. And so in population, due to strict convexity, if your model is misspecified, that is to say the true expectation, the historical expectation is not 0, then you cannot reach the minimum 0. You have an implied change of measure which gives you a strictly positive minimum, because it is only when it is well specified that you have a 0 minimum. Okay. The point I want to show you as quickly as possible is that if you allow for unbounded disaster risk, it cannot work. Because if I allow for unbounded disaster risk, it means that basically I can think, I have a non-zero expectation. This is my equity premium puzzle. And let me imagine that I can move in a kind of a small ball, for instance, around that as far as I want, far from the expectation. Okay, I'm sorry, I'm going very fast, but the slides will be available, I guess. Okay, and then what you realize in this case that your change of measure is going to be such that, it is almost always 1, but you have a small probability going to 0 to have a big disaster. Okay, and if you have a decreasing contrast, this is going to converge to 0, okay? Just by the fact it is decreasing. It is an argument actually that I'm borrowed from a recent paper by Chen Hansen and Hansen. And so the result of that is that there is no such thing as implied belief, because you can be as close to 0 as you want. You can build a sequence of change of measure, being as close as 0 as you want. And so you have a kind of impossibility theorem for any decreasing contrast, which is the case with empirical likelihood. That is to say, there is no such thing as a population counterpart of the implied probabilities computed by Julia and Gosh, which is, of course, worrying in terms of interpretation of their probabilities.
And Eric,
yes,
a couple of minutes left.
Okay, thank you, Issy. I'm going to try to do my best. So basically, we have to look at other Crest-Series families with non-negative exponent to be able to solve the problem. And to save time, I will jump to the solution. What you can show, it is something, there is an important paper by this Hungarian mathematician. These are about, what he calls generalized projection to compute the charge of measure as a minimum. It is a kind of a projection. And basically, under proper integrability conditions, it is true that you can find implied properties with Euclidean empirical likelihood, with clique, with any series divergence, when the exponent is non-negative, but it does not work with empirical likelihood. So my concluding remark, a couple of slides, I see of just concluding remarks. I have tried to give some, thanks to Infometrics, some quantitative underpinnings to this hypothesis of disaster risk, which will be hidden in investor belief. I have shown an impossibility theorem if beliefs are retrieved from empirical likelihood, or any decreasing contrast. So it cannot work. Sure, it can work if you are using non-decreasing contrast like chi-square distance or exponential tilting. The problem with that is that so it precludes empirical likelihood, and once this computation is useful because the model is misspecified, you will back out an implied participation which depends on the discrepancy measure you have chosen. So since empirical likelihood does not work, what measure should you choose? So, this casts some doubt about the validity of this approach. An alternative approach, which has been proposed precisely as the paper I was mentioning, is to compute instead a set of potential beliefs, because, there is kind of impossibility theorem in terms of identifying unambiguously an implied belief. When you cannot identify it, it depends on the distance, and there is no such thing, as far as I know, of a reason to choose one distance rather than the other. Okay, I'm going to stop here.
Super. Eric, I am really interested in seeing the draft paper. I'll try.
Yes, I'm glad to say. I would send you see that personally, and maybe also I most want to put something on the website. But there is a paper. There is a paper. So I'm going to send it.
Fantastic. So I haven't had time to digest, but there seem to be some overlap with the Epstein and Zinn attempt at higher order utility functions than power function to explain the so-called puzzle of the premium puzzle, and those utility functions look remarkably similar to the Cressy-Reed.
Yes.
So there are implications in terms of who's in a way making optimal decisions. And if we allow some heterogeneity, especially, then people have risk aversion degrees that would explain the outcomes. It's not so much just the beliefs, different beliefs or disasters, but it's just that a portion of the population has very high risk aversion, so it demands much higher return than the risk-free.
No, makes a lot of sense. I see a couple of quick answers on that. Number one, of course, there is a deep identification problem between beliefs and preferences, right? Because it's a product of the two which matters. Today, I have chosen to set the emphasis on belief. Of course, you can set the emphasis also on preferences, okay?
Excellent.
I have actually a paper about, state-dependent preferences, which may explain the puzzle, a paper in Review of Financial Studies. In terms of preferences, you're right also that if you start thinking about heterogeneity of preferences, it gives you a large degree of freedom. So to some extent, some rare extreme preferences can play the same role as my rare disaster. And in terms of heterogeneity, I remember some interesting work, I think, by a co-author of Duncan, if I am not confused. His last name was Toda. I have forgotten his first name. He had interesting work on what you can produce with heterogeneity of preference. Of course, you're right. See, there is a choice. You have to choose between preferences and belief. Today, I have chosen to set the focus on belief because it has been popular in the literature. The fact that people have in mind the possibility of rare disaster. So it's not because they're very risk averse. It's just because they have this in mind. Okay.
Anyone else? We have about 5 minutes. I extended the time a little bit because we started 2 minutes late. Any other comments? All right, we'll save a little bit of time. I should do some advertising here. In a paper with Vance Martin, we looked at dominance relations between indices and risk-free. And we find that the return distributions cross so early, there is no chance of dominance even at the third, fourth, fifth, sixth order, which sort of supports that idea that, well, there are people with very high risk aversion. The Mehra-Prescott idea of that there is a puzzle is not borne out by the data, as it were. And what's nice about this paper and the ones that we are talking about is it's trying to explain in various ways why we do have this risk premium, because we have it. Sort of average of 6% over 100 years or so. And so I'm very pleased to see this angle to why we observe it. Super.
Sanctuary. I'm going to stop sharing to leave the room to colleagues.
Superb. The next speaker is Duncan, no stranger to this crowd and any other. Duncan is talking about Bayesian quantum wave amplitude inference in EARN mixture models. Duncan, you have about 15 minutes starting now.
Thank you. Thanks to Infometrics and Amos for, can you see for setting
yes.
This up, and also his eloquent expression of how much we're going to miss Mike Dunn. This work is I have only a very short time, so I'll skip quite a few of the slides. But the basic, I just want to make 3 points really. One is that there is not as much difference between the way quantum theorists do probability and the way Bayesians do probability as you might think. And I want to show that formally. A second, okay, so that's the main message of the paper. I just wanted to mention a couple of sources of my conversations with Dave Oliver and Alice Scharfenacher, some correspondence with Frank Ladd. And if you're interested in following this up and are not familiar with it, there's a very interesting paper from 1998 by Fritz Frohner on the relation between classical probability and Bayesianism. So the purpose of this slide is just to establish the well-known terminology of Bayesian inference in terms of a hypothesis, data, a prior distribution over hypotheses, a likelihood, and a posterior distribution, which I'm sure people are familiar with. The main point of this slide is this remark that Bayes' theorem can be seen as a method for updating probabilities of hypotheses given new data, but it also is a method for making inferences about unobserved aspects of a system represented by hypotheses from observed data. And that's a theme that I'm going to try to develop. This slide just goes through the standard EARN model with the multinomial distribution. And since that's not the main focus of my interest, I'll just skip to the punchline of that, which is that when you do this with actual integer numbers, your hypothesis is a certain number of balls of each color are in the EARN. The posterior gives a positive probability only to integer values for the numbers of balls in the urn. So we seem to be, the data is going to be integers, and then you can also limit the hypothesis to be integer, but you don't have to do that. In fact, even though any observation or measurement we make is going to have a finite precision, and therefore we're really effectively dealing with a finite number of possible outcomes of any particular data generating process, you can entertain hypotheses that have much more complex structure to them. For example, you could think of a hypothesis that has real numbers in it, even though you're never going to observe a real number. All you're going to observe are intervals defined by rational numbers, because that's the way human life is. Or, as I'll try to show, you can even introduce complex parameters in this framework through the same process. So just as an example of this, I redo the urn problem for the multinomial distribution by assuming that the distributions are actually real numbers, which I'll call rho. I apologize for the fact that I've got rows and p's in here, but because the physicists use rows in exactly this sense, I wanted to keep that convention going. And this is the well-known derivation of the posterior probability. The point here is that although the data is limited to a finite number of discrete outcomes, the posterior probability gives probability to intervals of real numbers. So I just want to get that as the background to the introduction of complex numbers. In quantum mechanics, a very important question is the basis of measurement, because when you change bases of measurement in quantum theory, you change the type of information that you get. So I wanted to just introduce this idea of a change of basis in this context. It turns out that, in fact, if you change the basis, and both the basis in which you express the hypothesis and the basis in which you take the measurement, you find that the Bayesian posterior is in fact invariant. You get exactly the same form for the transformed posterior as you got for the original basis. This particular transformation is the Fourier transform of the original basis, which in quantum theory is the distribution of momentum, typically. So you get exactly the same outcome. And let me just discuss, though, an important difference. In general, there is a what's often called Hirschman uncertainty principle that links the entropy of the posterior of the hypothesis in the two bases, which is this relationship, the entropy in the original basis plus the entropy in the transformed basis has to be at least as big as the log of the number of outcomes. Well, you can see that that's very close to the to the Heisenberg uncertainty principle. You can also see that it's very formally very close by noting that the entropy of the Gaussian normal distribution, which is the usual assumption that quantum theorists make, in fact, is effectively the log of the standard deviation. But there is a difference, which is that in quantum theory, because there's a non-negligible Planck constant, you lose information in transforming from one basis to another, unless the bases now I'm just forgetting that word. Okay, anyway. So now let me just try to move on to the quantum probability in an urn model. The point that I want to make is that if you have two urns of different composition, as long as you can keep track of which urn each observation comes from, you can reconstruct separate posterior probabilities for each urn. But it's a quite different situation if somebody's bringing you the observations, but not telling you which urn they come from. This is effectively like the two-slit experiment that Ariel Katicha was mentioning earlier. So in this case, what you're going to have to do is either infer the composition of one big urn that you think of as the source of the observations, or you're going to have other possible ways of dividing up this information. So you have this problem of combining the hypotheses for the different urns. And this leads then to the question of the complex numbers. So if we want to describe an urn now by a vector of complex numbers, which we would call amplitudes in quantum theory language, these would be the square root of the rows, the proportions that we were talking about before, and in each case multiplied by a complex phase factor. These phe's will be phases. And so so you have not just a row one telling how many balls there are in the urn, but also a phase factor that's attached to each ball. You can interpret the non-negative squared magnitude of these amplitudes as the frequency with which that outcome appears in an actual sample. So the way you move from this hypothesis to what you can actually observe is through this Born rule, which is, as it's called in quantum theory, that says, okay, if you have this hypothesis, it predicts that you're going to see the balls in proportions corresponding to the squared magnitude of these amplitudes. Now, the first thing you notice from that is that when you square these magnitudes, you just get back row one through row k, because the square of any e to the I phi, any phase term, is 1 for all values of the phase. So if you're just pulling balls out of an urn, you're not going to get anything from assuming phases. The case where you will get something out of assuming phases is where you don't know which urn the balls came from. In other words, this is like the two-slit experiment, because in that case, you're going to make your prediction by taking the average of the amplitudes weighted by the frequency with which each urn is sampled, before squaring the magnitudes. This, in other words, is going to give you the interference effect that is characteristic of quantum phenomena. And if you work this out, for example, here's two urns with different composition represented by these amplitudes. You can see that what you get in the end is the weighted average of the number of balls in each urn, but you get an additional term which involves the difference in the phase between the two urns, if you want to think about it that way. This is the interference term, and it emphasizes the fact that this kind of reasoning cannot tell you anything about the phase of an individual urn. It can only tell you something about the relative phase of two urns that you're sampling together.
Duncan, I'm afraid maybe 1 minute.
Yes, that's fine. I'm pretty much at the end. So you can only make inferences on the difference of the two urns. You can take one urn as the reference urn and then look at the phase of the other, and I work out here the posterior probabilities. You can see that you will get an interference pattern in this. You can get an interference pattern in this case if you rotate the phases of the urns. And you can, in fact, compute a joint probability over the phase and the amplitude of each urn. I just finish up by saying that there is a paper that applies this idea to clustering and shows that the introduction of the phase element can improve clustering, because you're going to get a better resolution of clusters by applying this kind of phase reasoning to the clustering problem.
Thank you, Duncan. So we've got about 7 or 8 minutes for comments and questions.
I have a question. I have a comment.
And a comment, okay.
Yes, a comment. I would say that your approach to these things is very unusual, but that it seems to be working. It seems nice. But my comment is, you stated at the very beginning that the way Bayesians approach quantum mechanics is completely in agreement with the standard way in which we do probability. And you are completely correct. One of the weird things about quantum mechanics is that people think they have to invoke these weird concepts of quantum probabilities. And you're completely correct that if you know your probability properly, you don't have to do that. Just knowing what it is that we do when we do probabilities, namely a Bayesian approach, maybe sprinkled with entropies here and there, it solves the problem. So I agree with you, Duncan. That was my comment.
Well, maybe this is preaching to the choir then, but at least that message gets through to Ariel. Does anybody else have a question?
Yep. Have you given some thought to entanglement?
Well, that's no. So far, I've just been concentrating on trying to see which elements of the interference problem can be developed at the level of these classical models. Because this is a completely classical model. This urn model has no Planck constant, has no significant Planck constant to interfere with the elements. I am pretty sure, but it's a guess, and I hate to make guesses, that in this framework, you can actually reproduce something like entanglement, but I haven't done that yet.
Right,
So-
thanks to
So what
Duncan.
is
Yeah,
the source of the interference then?
Well, that's an interesting question. If you think of the balls in the urn as having a phase, for example, suppose a ball in the urn has a phase of minus pi. This phi1 is minus pi. Well, that essentially means that it annihilates a ball that has a phase of plus, of 0, let's say. So when you start counting the balls, those two balls are going to disappear.
But they're not interacting. They're just statistical disappearance. Is that what you're
That
referring?
would, yes, this is all purely formal because, you know, if we're thinking about colored balls in an urn, I mean, I've tried to think of plausible examples. I mean, but they're a little bit fanciful, that you have a green ball and a red ball, but some of the green balls are very faint green balls, or some of them are actually negative green balls.
all right. I'm going to thank Duncan and move on to the paper by Amanullah on flexible information theoretic approach for inference in the multiple regression function and for marginal effects. I'm translating the title. Aman.
Yes, please bring. Okay, can you see that?
Not yet.
Not yet.
Not yet. Okay.
Do the share screen and
Okay.
pick what you want to share.
Yes. Very good. Oh, just 1 second.
So if you clicked on what you want to share and then say, okay, oh, we
Okay.
just saw it. Good, 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 good. Here.
Here we go. Okay, so thank you very much. And this paper is joined with the. Oh no, this is the wrong one. Okay. Go back. Right.
Good, we can see it.
You can see that?
Yep.
Okay. Well, okay. Sorry for that. So this is a joint paper with Amos and my colleagues over here. And so the basic aim here is that in econometrics, you basically try to estimate or analyze density function, regression function, this derivative, which gives you the marginal effect, and conditional variance function and other functions and that. And whenever we do that, we make some assumptions about the functional form, and then we proceed with the analysis. But here we're looking at the flexible specification of those functions, particularly the regression function, and then get the marginal effects but the other function can also be analyzed with the help of entropy. So that's the main purpose. And this paper by Shannon, which he wrote in 1948, the mathematical theory of communication. That's which James used in order to generate the density function. So that we will use in order to develop the regression function. And as you all know that this is the month when Shannon was born. So this is 105th birthday, and he was born in 1916 in Michigan, died in Massachusetts at the age of 84. And these are some papers which are related in entropy. And then I will compare this with the entropy-based regression and derivatives with the non-parametrics approach, which has developed over the years, the kernel-based database. And so basic idea is that if you have this regression function, where the regression function is the average value of y given x, but statistically speaking is integral of y and joint density over fx. And you have to know this joint density and marginal density. If you assume normality, then this and then you write over bivariate normals, then you will get the alpha plus x beta. And that's how the parametric econometrics developed over the years by assuming that parametric. And then if instead of joint density to be normal and going into the parametrics, you use the kernel density of F5, the database, kernel density of Rosenblatt, then you will get the non-parametric regression function of the, okay. So that's what happens, assume normality, then you have linear regression. If you have this joint density database, if you use that, then you will get this Medley-Watson estimation of the non-parametric kernels. And so I will compare with these things. So if you look at this Shannon's entropy, which is an average information in the variable X, and what James did was maximize this with respect to this moment conditions. I've used the general moment conditions, but if you take moment condition x to the power m, so capital M moment conditions you have, then the James density function for the one variable x is basically this using this Lagrangian minimization, maximization. Okay, so this in this density, this is exponential. Lambdas are basically this Lagrangian coefficients, and phi is the moment condition. If the moment condition is x to the power m, so it will be that. And of course, when you substitute this in the Lagrangian, then you can get the Lagrangian function of lambda, which is basically weighted sum of lambdas and the moment conditions, which is the you have. And so when you get this lambda for m greater than or equal to 3, you can get the lambda from here substituting in density, then basically you have got the James estimated density function. You can extend this for the joint density also, because we need that at least. So joint density here subject to these moment conditions, and I've taken here not capital M number of all possible moments, but suppose I take the 4 moment condition, you can do it for any number of moment condition you can have. Then the joint density you get is this, and the moments conditions are basically this kind, Fm1 and Xm2. So with this joint density function, we can you can rewrite the function, simplify, and the lambda can be obtained from here. So therefore, you have the estimated joint density given by James. Okay, I can rewrite this and then you can get the marginal density from here. So marginal density and the joint density depends upon the lambdas. All the number of moment conditions will be equal to the number of lambdas you will have. And they are all estimated. So that's fine. So you have this density, James density. So what happened then is that the Shannon's Bayes, this using this James density, you have a regression function, which will be the integral functions of that. And you don't have an explicit solution of this, but they are an integral representation in terms of y and x. And so when you are calculating the regression function based on the Shannon, so you have these lambdas are already estimated. So you have to get this integral. So the mx is, the ratio of the integral functions, and these integral functions depend on lambda. Lambdas are already estimated, so your lambda hat, and so you have to get this integral. So what we did is develop a algorithm to calculate these integrals recursively. And the fantastic thing about every point x, I got my mx by doing this numerical integration. And so we get the this regression function based on that. And using that integral algorithm which we develop, and is a recursive. Once you get for one values of x, then recursively I can get for other values of that. So that's, and then if you take the derivative of this, then that will be marginal effect, and that's, you can easily obtain the derivative of these things, and that will also be integral function, and you can calculate the derivative, which is beta x. And and then we show that this estimator is very flexible because we have used this moment conditions, and it is also consistent because lambdas, these Lagrangian coefficients, as a function of the moments, and the moments can be replaced by the sample moments. Therefore, this lambda hash will be root n convergent because these are function of the sample moments. And because the lambda hat is root n convergent, the numerator and denominator, each one will be root n convergent. They are functions of the lambda hat. And therefore, the m hat, the regression function, is also root n consistent and root n normal. So we just proved all this theorem, and that this regression is root n consistent. And we don't have time to tell you this integral, but and beta also is a derivative of m, so that will also be root n consistent. So that's well exciting, and then we try to see, how it works. The Shannon-Bayes this regression function and the derivative of that. And so I just take a simple example in simulation, this nonlinear function, and then I wanted to compare with linear, which people use, and the quadratic people use, and then non-parametric, which is a non-parametric kernel data, which expanded in recent years and very popular. So, and compared with that, this Shannon-Bayes regression function, and it showed that this beta, this basically, and then get the derivative of that. So the Shannon-Bayes regression function is derivative based on that. For this simulation is 0.667. No, this is the true value because the function is known, so I can take the derivative and do 0.667. And so if you do the linear, is of course it's biased, and it's quite much biased on 0.66 is the amount of the true value, and the root is mean square is very high, and quadratic is also biased because the function was the exponential in simulation. And then we look at the maximum entropy derivative of the function at the x is equal to 0.5 because x is uniform. The maximum entropy was 0.6550, which is basically close to 0.667, which is a true value. But when I did the non-parametric kernel, which is supposed to be picking up the bias well, in other words, is normal should be, still its bias is higher than the maximum entropy, and the mean square error is also much higher compared to the maximum entropy. So I was very shocked and surprised that it was beating the non-parametric, which is a data-based modeling, and it does, and also calculate the mean square error. But it is true that the non-parametric, of course, the linear and quadratic can be specified for this model because this is an exponential model I've taken. So that's obvious, but non-parametric is a bit, that's also beaten, so I was surprised, but then that's why we try to prove the results and show that our maximum entropy is root n convergent compared with the non-parametrics is not root n convergent. And so slow speed of convergence, and so it has a higher variance, even though the bias may be small. So that's why we can beat that. So that was very, then I tried to see how it works in the real world data. So this is a 1971 Canadian data on log earning and age. And I use this Shannon's entropy based my regression function. It gives this result. So, and this is fantastic because there's a dip around age 45 and 50, which is expected in this data because the 35 years ago, because of this world war effect and also the recession and all that, this is that generation of people who had the dip in this data. So
Aman,
yes.
Aman, you have -1 minute.
-1. Okay, I will take -1 more. So I think so this is the correct result, and it's also known that 1971 data, it is more quartic rather than quadratic. So the earnings function is known to be quadratic by Heckman and all those kind of things. That's not true. Actually, for this data and many other data I've tried in this paper. Okay, so that's the, and then the last one I will show because to make it. Okay. Okay, and the results have been generalized for any number of x, multivariate case. But and the other, this is a Coop and Tobias data on log wage and education and experience to have two variable case 2001, around 2000 observations, and the joint density gains was turned out to be this. And of course, we also do this lasso kind of selection of the number of moments we should have. It was for two variables, but 35 total moments. But by lasso, I got the 10 moment condition. So that's why there are 10 lambdas over here. And I did this out of sample predictability using this Monte Carlo cross validation, MCCV. 80% of the data was, fixed as a training data, 20% validation data, and then we got the root mean square error for the 20% observations, and this there. And then do the bootstrap 100 times, and then you take the average mean square error of this. Look at this. If you do the linear model for that earning function, root mean square 0.49, quadratic 0.4917, and then maximum entropy was 0.322. And look at this non-parametric, both local constant and local linear estimation is much higher than the maximum entropy, even in this two-dimensional case for the predictions purpose. So
All right.
this is a direction in which I think Shannon entropy can be used to develop a flexible regression function. for future generations. Okay.
Super. Just a quick comment. I know you know about the work that Nick Kiefer and Jeff Racine did on looking at the information gain that is implicit in doing non-parametric. And that might shed light, or at least provide a nice point of departure when you compare your non-parametrics with the maximum entropy results. It looks like maximum entropy somehow is more variance reducing, whatever the information is using, compared to smoothing that is done with non-parametric.
No, yeah, that could be reason. And I gave this, that is a good way to see it. And the other is also because I think the rate of convergence. I think if you have, that will give higher variance to every time you do the non-parametric. Because in non-parametric, you're trying to get the infinity of parameters, you're trying to estimate. So therefore, any data you have, you will lose more variance efficiency. And even though the bias may be nice and small, but the variance will be high. And so I think there's a tremendous scope of the Shannon to be used in developing the econometrics in general. And
I should also selfishly mention that you can deal with missing data rather nicely, because once you've got these distributions pinned down by maximum entropy, you can draw anything from them that is missing. So it's a very natural solution to missing data in this setting.
Yes, that's a good point. We haven't looked into that at this stage.
So a couple of minutes, we are over time. It's after 1:30, but if there are a couple of questions, at least one question.
Just a short comment. Oh, sorry, I see that Duncan has his hand up.
Since you're the
I just had
co-author,
a clarifying question. What do you call local LL in your last slide?
That is a non-parametric, it's called local linear.
Is that the same as what is sometimes called low S?
Yeah, low S. Low S is also.
Low S is, yes, okay, that's my question.
Cleveland and all that, they call it low S, and this is also similar, local linear, right?
Okay.
Yeah. So
almost quickly.
Just you mentioned gaining information in your mentioning of Nick and Jeff. What do you mean gain with respect to what?
So they look at what is the implicit information that you're using in kernel smoothing. It's an idea that Jeff and I had talked about forever, because there is implicit information when you do non-parametrics, right?
Oh, of course.
And so you can measure that by entropy. And here we know how these moment conditions, side conditions inform the maximum entropy distribution, but they're different side informations. That's the point. Different side information. All right. Okay, we thank all three speakers. Thank you for staying within time limits, very severe time limits. And so I guess I'll pass it on to Amos for the next session. Thank you.